so for this first one, you might want to just draw like a little picture. It's not important that it's neat. Just you have 4 objects, A, B, C, D, right? And the charges, I'll put in red, they are basically 1Q, 2Q, 3Q, and 4Q. So I don't know what Q means. Honestly, I don't. Maybe Q is, 1 Coulomb. Maybe Q is 90 coulombs. All I know is the relative charges between these. So I know the first and fourth objects have the fourth object has 4 times the charge of the first object, is the idea. Okay, so when sphere A bumps into sphere B, what happens when these two bump into each other? Because that's the first thing that happened. Well, you would say that charged sphere B, right, is going to have more charge than charged sphere A. So, but when they come together, there's a total of 3Q charge there, right? There's 3Q charge there. So what do you think is going to happen? The electrons are going to basically all kind of start spreading out, right? So you have these 2 balls. There's a total of 3Q charge. They're going to try to get away from each other. And now that the conducting spheres are touching, they have a path to follow. So they're going to start racing all over those 2 spheres and spread out as evenly as they can. So I'll pause the recording. So this is going to get split up evenly into 1.5Q and 1.5Q. Okay, so now this is sort of phase 1 of the journey. Both A and B have equal charge now. So these are now separated. Let's just assume they bump apart. I probably should have said that. And then B goes along and bumps into C. Okay, so fine. B comes along and accidentally bumps into C. So let's draw our arrows in red, huh? So our interaction arrows are in red. So these come together. So B had 1.5 and C had 3. So they bump together and they form 4.5Q. But there's conducting spheres, and the electrons are going to immediately try to spread out and get away from each other as best they can, distributing themselves evenly across spheres B and C so that each sphere has half. So what will each sphere have? Okay, so now we have a third scenario. B no longer has 1.5. It has, B and C don't have 1.5 and 3 anymore. Sphere B now has 2.25Q, and sphere C has 2.25Q. You see? Okay. There's one more interaction, but it looks like charge A is stuck. Charge sphere A has 1.5. There's nothing we can do about that. Charge B is no longer going to interact, so he's stuck with his 2.25Q. But charge C has one more journey to make. So charge C now is going to come up and collide with charge D. And when charge C meets charge D, they're going to share their charge. So we have a 4Q from D and a 2.25Q from C. So there's going to be 6.25Q to share, and they're going to share it evenly because they're touching. And so it's going to end up where basically it's going to look like this. Sphere A is stuck with 1.5Q. That was from his first bump into sphere B. Sphere B had 2.25Q. And spheres C and D are going to share that 6.25 evenly. So that's going to be 3.125Q each. Okay, so language-wise, I made this question a little bit easier, but concept-wise, this is one of the concepts you have to understand. The distribution of charge equally throughout the conductors. Okay, now if I brought 3 things together at one time, then what you'd have to do is add up all 3 and then divide by 3 to see what each one gets. In other words, you're going to average, right? If there's 1,000 charges and they bump into each other, you're going to add up all their charges and divide by 1,000 to see what each sphere gets. So just average the interacting spheres to see what each sphere ends up with. Okay, that's the first math problem. All right, now let's go on. I should not have erased my answers. I need that for part B. I think I remember them. I have to erase for space reasons, but I will need those answers here. This one already has the answers on it, so let me erase those real quick. We'll get to the answers in a minute. Okay, now if all of the spheres are suddenly tapped together, what is the charge on each sphere? So now all four spheres are going to come together, happily bump into each other. Let's see what happens. So remember what they had originally? After the last problem, it was, what was it? 1.5, right? This one was 2.25, and these were each 3.125, right? Okay, so how much charge do they have all together to share? So this makes 6.25 plus 2.25 is 8.5 plus 1.5 is 10. So there's 10Q to be shared throughout. Now, how did I get that 10Q? I added the 1.5, the 2.25, the 3.125, and 3.125Q, right? Can you think of another way I could have gotten the 10Q? Suppose I didn't do part A. How could I still have known that there was 10Q to be shared? Okay, you also could have gotten the 10Q just by adding the original 1Q, 2Q, 3Q, and 4Q. Okay, now if these all bump into each other simultaneously, then they're going to transfer their charges 4 ways evenly. So each sphere is going to end up with 2.5Q throughout. Okay, let's go to the next one. All right, now it says 2 more things happen now. Spheres B and C are intentionally grounded. Ooh, okay, this is different now. Now we're bringing in a ground. So the charges were, all the charge spheres were 2.5Q, but spheres B and C now have charge 0. When you ground something, it loses its charge. Its net charge anyway. So we had sphere A, B, C, D. They all had 2.5Q. But that grounding effect, when you touch those spheres to the ground, they lose their charge. So these are now 0 charge. They're zeroed out. Okay, and it says, after that, A and B are tapped together, and C and D are tapped together. Okay, so let's see. A and B are tapped together. So they're going to be combining their 2.5Q and their 0Q together. And each one's going to end up with what? What's going to happen there? So A is going to end up with 1.25Q, and so is B. Remember, they share it evenly. Meanwhile, C and D are also tapped together, so the same thing happens over here. So now C has 1.25, and so does D. So everybody has 1.25 charge. And lastly, we tap B and C together. Well, that does nothing. B and C are relatively neutral. They're not neutral, but to one another they are. You know what I mean? They both have 1.25Q. So you put them together, you have 2.5Q, then you divide by 2 again to split it up evenly, and you're back to 1.25Q. So the charges are 1.25Q, 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 1.25Q. So that last one was kind of silly. The B and C tapped, but nothing happens because they're equally charged. All right. Let's go now to our next example. And we're getting a little low on time, so I don't know if we're going to finish all these, and that's okay. Okay, now we're talking about forces, not just charge distribution, but forces themselves. So you're going to be using that KQQ over R squared rule a lot. R is just the distance between their centers. Okay, we have charged particles A, B, C, D, and E. They're charged with Q, negative 2Q, Q, negative 2Q, and Q respectively. Okay, what is electrical force of A on D when A and D are 1 nanometer apart? What about if they're 2 nanometers apart? Okay, so remember, a nanometer is times 10 to the minus 9th meters. Okay? It means billionth of. Nano means billionth of. So sorry about the silly prefixes we use. Okay, so anyway, you're going to be using KQQ over R squared. KQQ over R squared. And the r is literally the distance between them. So you just do 1 times 10 to the minus 9th. So this is for the 1 nanometer case. Well, what are the charges? Don't think Q and Q. Think what are the actual charges in this problem. Well, you're doing force of A on D, which incidentally is the same as the force on D and A, on D from A. So whether it's A pulling on D or D pulling on A, Newton's third law says it doesn't matter. Just let's make sure to use charges A and charge D. Like, make sure you use the right two charges, is what I'm saying. So make sure you use Q and negative 2Q. So don't just put QQ here. Put Q and negative 2Q. So when we put Q in the formula, we really mean the total charge of those objects. Okay, so you end up with basically on the top, 9 times, we said it was 9 times 10 to the 9th, remember? That's K. Then there's a negative 2Q squared. And then on the bottom, we basically are squaring that, so we end up with 1 times 10 to the minus 18th. You do not need a calculator for this, and you don't need units. It's going to come out to newtons, trust me. Okay? So the top is 9 times 10 to the 9th, but you're multiplying by negative 2, so that's negative 18 times 10 to the 9th. And there's a Q squared. We'll never know Q, so too bad. The bottom is 10 to the minus 18th. You don't need the 1. So dividing by 10 to the minus 18th is the same as adding 18 to your 10s on top. So you end up with negative 18 times 10 to the 27th Q squared. Or in scientific notation, you'll have to move the decimal back a space, which means you get to add 1 to your power. So it turns out to be negative 1.8 times 10 to the 28th Q. So again, I don't know what Q is, doesn't matter, but this is sort of the force that we feel. Go ahead and put newtons, it's a force. Newtons. Now, what happens when we move them 2 nanometers apart? Listen, I don't want you to recalculate. I really, really, really don't. I want you to think qualitatively and quantitatively here. So, yeah, you're going to lose 4 times because on the bottom there's an r squared, right? So basically when the bottom has an r squared like that and you end up doubling the distance, this is very important, especially those who haven't had physics yet. Okay, listen. When you put in a 2 here, that gets squared. This is an inverse square law. So you're going to end up with a 4 right there that wasn't there a moment ago. All that means is now you have a 4 on the bottom that wasn't there a moment ago. And that means it's going to cut your force down 75%. So it's going to be 1/4 of what it was. That's how you want to think in physics. Don't recalculate ever. Okay? Ask what would happen if I changed this or that or the other. Okay, so let's write our 2 answers. It was negative 1.8 times 10 to the 28th. Q. The reason I didn't choose Q, by the way, I didn't want to say what Q was, is because if Q is 1 Coulomb, this is an extremely large force. You know what I'm saying? So I just wanted to have realistic numbers, and I wasn't sure what to make Q to make that happen. So I'm just leaving Q in my answers. So this is when they're 1 nanometer apart. But if it's 2 nanometers apart, then it's just going to be 1/4 of that. So negative 0.45 times 10 to the 28th. Or you can move the decimal over a space, and then you get to subtract 1 from the power. So it's going to be negative 4.5 times 10 to the 27th cubed. This is the 2 nanometer case. What's the big takeaway here? When you double the distance, you 1/4 the force. And that's true in gravity also. You go twice as far away from a planet, and you experience 1/4 the gravity. That's why it gets easier and easier to leave Earth. The further away you are, the easier it is to escape gravity. Correct. Student corrected me. These are both Q squareds. Thank you. Okay? All right. Now, what is electrical force of A on C when A and C are 1 nanometer apart, 2 nanometers? This is the same exercise. It's the same exercise. The difference is, this time we're using charges A and C. So can you guys tell me one thing that will be different here? Okay, so it does mean, yes, that you'll have opposite signs from before. So these were negative, meaning there was an attractive force. This is a repulsive force. You have 2 positive charges repelling each other. Now, do we have to redo? Do we have to recalculate everything? What do you think? This time we're going to have K, Q, Q over 1 nanometer squared. Well, this is the same calculation we did back in part A, except the top used to say K, Q, 2Q. So we're missing a factor of 2 on top. I don't think we need to retype this, do we? It's going to be positive this time. And we don't have a factor of 2 on top that we did before. So it's only going to be 0.9 times 10 to the 28th. Q squared. That's the 1 nanometer case. So see how I'm saving time by not recalculating? Because last time there was a K, Q, and a 2Q on top, dot, dot, dot. And now there is no 2 on top. I'm just assuming that the answer for the first question on part B is just half of the answer for the first question on part A. So we're trying to not really recalculate if we can help it. And then the same thing happens. When you go to 2 nanometer case, the force gets cut down to 1/4, right? So now what's 1/4 of 0.9? It would be 0.225. Okay, so 0.225 times 10 to the 28th. Both these really should be put into scientific notation. Remember, scientific notation is where you have right here a number between 1 and 10, which we do not have actually. So let's fix that real quick and we'll move on. So this, if you move this over one space, it's 9 times 10 to the 27th, Q squared. And this one, you'll move it over one space. Since you're moving to the right, you steal one from the tens. So it's 2.25 times 10 to the 28th, 10 to the 27th. Q squared. And these are all newtons, 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 newtons. And you know that's important, right? You're not going to go take an AP test, please, without mentioning the units. I hope, I hope, I hope. So let's go back in here. Newtons, 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 right? Everywhere. Capital N's fine. What is the electrical force on C if A and D are 2 meters apart and C is halfway between them? Okay, so it's getting a little more complicated. We'll talk about that one next time. So I'm going to post this document online so you guys can